So this is a tutorial on simplifying ratios, and the ratios in question, we're not going to deal with fractions, we're looking at part-to-part ratios. So the normal kind of ratio when you've got some whole number which is broken into two parts. So let's just think of an example to start with. What if I have 33, could be 33 degrees, or it could be 33 objects. But anyway, it's been broken down into, let's say, 6 and 27. So these lengths here aren't representative. I'm just using that as a holding form so I can fill in my numbers and say, well, 33 has been broken up into 6 objects and 27 objects. So for example, it might be that we're talking about things that have been sold versus things that haven't been sold. So 33 products have been sold, are on sale rather, only 6 have been sold, so we've got 27 left. So the question is going to ask us something like, well, what is the ratio of sold items? So if these ones are sold, okay, to unsold items, so these ones are unsold. So it'd be that sort of real world context that they tend to give you in maths tests and puzzles and problems. Okay, so we've got 33 and we've got a 6 to 27 ratio. Now, a ratio we want to always express in its simplest form. Now, 6 to 27 is certainly not the simplest form. Now this is very easy. You can see that both of these numbers we can divide by 3, and that will scale it down to 2 to 9 ratio. So our answer we're going to get here is 2 to 9. But I'm just going to think about, well, how did I get that? What I must have done is I must have multiplied by a scalar, but it's got to be a fractional scalar. So if I think of this algebraically, when we're scaling up, so if we start with 2 to 9 and we scale up, what do? We write 2n plus 9n must equal the total, which is 33. And so we simply add this together to get 11n, and then 11n equals 33, and so n equals 33 divided by 11, which equals 3. So n is 3, and that is how we would scale up to get our 6 to 27 if we were scaling up. At this time we're scaling down, so we can think of it as n, but when we're scaling down, it's a good idea to think of it as 1 over n, or the reciprocal of n, because we're scaling down, not scaling up. So in other words, what we're doing is we're dividing by an unknown scalar. We're dividing by n. So 6 times 1 over n is the same as 6 dividing by n. 27 times 1 over n is the same as 27 dividing by n. So our question here, just like when we were scaling up, this time when we're scaling down, we're asking ourselves, well, what is n? Okay, what's the unknown value that we're scaling down by? And of course we know it's 3, but how do we find out that it's 3? Well, the answer is we use methods to find the highest common factor. So it's an HCF problem. So in other words, to find n, we need to find the highest common factor of 6 and the highest common factor of 27. And if we list out the factors, we end up with 1, 2, 3, and 6 for 6. And for 27, our factors are 1, 2, not 2, sorry, 3. 2 will not divide into 27 and give us a whole number. 9 and 27. And so just listing out the numbers is a very simple and effective way of finding which of these are common, and if we had several numbers that are common, we would just find the highest common factor. The highest one here is 3. So the HCF of these two numbers, 6 and 27, is 3, which means that n must equal 3. Okay? So therefore n equals 3. So our ratio is 6 divided by 3 to 27 divided by 3. And 6 divided by 3 is 2. 27 divided by 3 is 9. So that's the method. Let's call this problem A and have another go with a slightly trickier problem, giving us more interesting numbers to work with for problem B. So, off the top of my head, let's think, if I double, I'll end up with 889. Okay, so I've now got 889. So, same sort of idea as we had before. Let's erase these here. We've now got 889 as our total. I'm going to split that again into 2, just as we'll do 3 in a minute, but I think for the moment we'll just stick with 2. So let's have a large number now to start with. So 784, and then 889 minus 784. Again, if we think of the soled idea, or if we think of any sort of quantity, maybe an area, we're often given two numbers. If we're given a total and just one of the numbers, we simply subtract from the total. So 889 minus 784, very easy, is 105. Okay, but what they want us to tell them is the ratio, 784 to 105. How do we do that? Scale it down. Okay, so divide by some unknown. In fact, let's change this so it doesn't have to be n. Let's call it k. Any letter representing a whole number scalar. So we're scaling down now. So if we think about our HCF, we could list, going right along here, all the factors of 784, and I suspect there'll be quite a few. So another method, and I think we've covered this in a previous video, is simply to break down using what we call prime factorization. So just to remind you of how to do that, 784, we want to pull out any prime factors, and when we've got an even number, we know we can divide by 2. So let's start with 2. And we've got 700 divided by 2 is 350. 84 divided by 2 is 42. So we've got 892. Sorry, 392. Okay, 392. So it requires a little bit of mental arithmetic. But of course, at every stage, you want to multiply this up. So 2 times 392 does indeed make 784. Again, pull out our 2 if we can. You can do it by long or short division, so just like bus stop method. So 2 into 3 gives us 1 with a remainder of 1. 2 into 19 gives us 9 with a remainder of 1. 2 into 12 gives us 6. So we've got 196 now. So that's perhaps a more reliable method, just to divide in as if you're doing the bus stop method. So 2 into 392, just like that. Okay. So now as we go down our tree, it gets a lot easier. So we've got 2 into 19 now. Well, that's going to be 9 with 1 remainder. 2 into 16, that's going to be 8. And just again, a check. 2 times 98 will give us 196. Okay, we can still divide by 2. So 2 again. We got 2 into 9 is 8. Carry 1. 2 into 18 is 9. So we've got 89. Sorry, 2 into 9 is 4. So we end up with 49. Okay, 49. There we go. And 49 divides, well, 2 won't go into it, 3 won't go into it, 5 won't go into it, but 7 does. So we've got 7, 7. So there are prime factors. So 2 times 2 times 2 times 2 times 7 equals 784. 105 is a lot easier. 2, no. 3, yes. So 3 into 10 is 3 with 1 remainder. 3 into 15 is 5. And here we've got 3 won't go into this, 2 won't go into this, 3 won't go into it, 5 will though. So we've got 5, and 5 into 35 is 7. So our highest common factor, our only common factor in fact, is 7. Just circle those. So the HCF of 784 and 105 is 7. So now we've got to replace K by 7. So if we write the ratio is, let's see then, 784 divided by 7 to 105 divided by 7 equals, okay, again by long division, you don't need the bus stop symbol, so 7 into 7 is 1, 7 into 8 is 1 remainder 1, and 7 into 14 is 2, so we've got 112. 7 into 10 is 1 remainder 3, 7 into 35 is 5, so 5 sevens are 35. So there we go, 112 to 15 ratio, and it's worth just checking because it sort of looks like that might simplify. Could I divide that down any further? Would 3, for example, divide into 112? And a simple divisibility check is when you add the digits together, 1 add 1 add 2 gives us 4, so we know it doesn't divide by 3, and so as long as we're reasonably comfortable, that should be the correct answer. Using the HCF method should have got us the correct answer, but just a little check just to make sure that that is correct. Okay, let's do one more. What if we had, let's think, 731, and now we've got 391. And 391 from 731 is going to give us 340. Okay, so those are the numbers that we're going to now work with, 391 and 340. You might want to pause the video and give this a go yourself, and then come back and check with the worked solution. Okay, so first of all we want to find our HCF. Again, the listing method might be long and laborious, so if we go for this method, now actually this is a quite nasty number. I can see using divisibility checks, and if you don't know what I mean by divisibility checks, worth checking that out in another video, but it means that you can look at numbers and you can see what will divide into it. And 391, let's just make that a bit clearer. I can see that 2, obviously 3, 5 won't go into it, 7 won't go into it even. Okay, so if I just subtract 2 times the last digit, 7 won't go into it, 11 won't, 13. In fact, the only thing that would work, I think, is 17. Yeah, so 17 should go. So that's good. Now, again, a bit of division to get the other factor here. So 17 into 39, well, that's going to be 2, gives us 34, remainder 5. So remainder 5, so it gives us 17 to 31 is 23. So we get a 3. 17 to 51 is 3, so 23. And 23 is definitely a prime number, so really I've only got two factors. 1 and 391, of course. Let's just erase that working so we can see that. So 1 and 391, but the other factors are 17 and 23. Okay, let's now work on 340. But what I really want is one of these two factors to go into 340. So whatever I do with prime factorization, I'm not going to get a common factor. I do want 17. So I'm going to write 17 down straight away. I can see that 17 goes into 34 twice, and then add my 0. So 17 times 20 equals 340. Does it? Yes, it does. So I've now got two factors that are going to work. I know what my common factor is. It's going to be 17. Definitely nothing higher than that, so that's my highest common factor. And now all I need to do is divide by 17. So my constant, whatever I call it, I'm simply replacing my constant, let's call it m, my constant m I'm replacing with 17. So now I've got my ratio. All I've got to do is divide 17 into 391, or 17 into 39, we've already worked out, is 23. And 17 into 340, we've already worked out, is 20. Again, as a last minute check, I'm going to just look at these numbers and make sure they don't break down any further. So I can't think of any number that breaks down that would go into 23, because I know 23 is a prime number. So I'm going to say that ratio is correct in its simplified form. Okay, so finally, let's just remove these and replace with a three-part idea. So we've now got a part to part to part. And if I think of some numbers that are going to work nicely here, let's start, in fact, let's use degrees. Okay, so very often this does crop up in exam tests and so on. So when you've got an angle, a straight line, in other words, like this, and you've got an angle broken up with two lines here, and you're asked what is the ratio of this to this to this. So you've got three angles, and the total is 180. So if I write down 180 degrees, okay, let's break that down. Let's think into 15 degrees, 69 degrees, and 96 degrees. Okay, and again, if you think you can give that a go, good point to pause the video and see if you can work out the ratio then. The simplified version of 15 to 69 to 96. Okay, so we're going to divide, again, we're going to scale down by dividing by some unknown value. Whoops. So there we go, sometimes that comes up. Okay, so divide by some unknown value, let's call it r. Okay, so what's r? What's r going to be? Well, again, if I use We could use a listing method on this, in fact, that would work quite nicely. Let's use prime factorization as well though, just to see if that works. So 2 won't work, 3 will work, and we've got 5. So we've got 3 times 5. For 69, 2 won't work, 3 will work, so we've got 20, 3 into 6 goes 2, 3 into 9 goes 3, so we've got 323s, and we've already worked out that that's a prime number, so that one's done. 96, let's put our degree symbols here. Okay, 96, we've got 2 won't work, 2 will work, so 48, so 2, 48, so 2 again, 24, 2, 12, this breaks down nicely, 2, 6, 2, and finally 3. So what are our common factors, and what's the highest of them? Well, there's only one common factor again in this situation, so we've got a 3 here. All of those 2's are not common. We've got a 3 here, and we've got a 3 here. So our highest common factor should be 3. So HCF equals 3. Let's just write that down. HCF equals 3. Make that a bit neater. Okay, HCF equals 3. So R equals 3. So now we've got our ratio is 15 divided by 3 to 69 divided by 3 to 96 divided by 3, which equals 15 divided by 3 is 5. 69 divided by 3, well, we've already done that, that's 23. And 96 divided by 3, well, one way of thinking about this, you could easily do bus-stop method, but is to look at what we've got left here. So we've got all these 2's, which multiplied together must give us our answer here. So 2 times 2 times 2, that's 8, times 2 is 16, and times 2 is 32. So you've got 2 to the power 5, you might want to think of it, is 32. 32 times 3 will give us 96. And again, just a quick check, will this simplify any further? Well, 5, there's no common factor, 23 is a prime, so quick check, and we can see that this must be the answer. Okay. Okay, so lastly, what if we had a problem like this? So let's say, instead of working it out in the same way as we've just done, I'm just going to write down a ratio here now. So this time I've got 1.8 to 1.2 to, let's say, 3.8. So here's another kind of problem, which is that we've now got numbers after the decimal point, and so what defines a simplified ratio is that it's a whole number, that it's an integer or a set of integers that are part to part to part. So we want to get it down to integers, and so this wouldn't be counted as a simplified ratio. So how do we simplify it? What do we do? Well, the very first thing I would want to do when I've got decimal points is just remove the decimal point. Okay, so we could think about this in terms of R like we did before, but I think the very first thing, the sort of natural thing to do, is to remove the decimals. So in other words, what we're going to do is scale up before we scale down. Okay, so if we're going to scale up, the number that we're going to scale by should be obvious by the number of decimal points that we've got, so number of figures after the decimal point. And with this example, we've got only one figure after the decimal points. In other words, each of these numbers involves tenths. If it involves tenths, then if we multiply by 10, that will remove the decimal point. So I'm going to multiply through, so scale up by times 10. Okay, so then I've got 1.8 times 10 is going to give me 18. 1.2 times 10 is going to give me 12. And 3.8 times 10 is going to give me 38. So you can see you've got the same digits here, but all we've done is remove the decimal point effectively by scaling up by 10, giving us an 18 to 12 to 38 ratio. Okay, and now we just proceed as we did before. So if we think of any number, let's say x, to scale down now, then we're going to think of x. What is x in this situation? What's the highest common factor? So again, if I move over to one side, I think of 18. That's going to be 2 times 9. And then I pull out 3 times 3. So it's 2 times 3 times 3. Let's have a look at 12. That's going to be 2 times 6, and then that's going to be 2 times 3. So 12 is 2 times 2 times 3, and now 38, and that's going to be 2 times 19. And so 19 won't break down any further, so my highest common factor is in fact quite low. It's 2. So all I can do now is halve this. X must equal 2. So x equals 2. And halving it should simplify as much as it can be simplified to 9. Let's write it out fully so that it's very clear what we're doing. Okay, so 18 divided by 2, which is 9. 12 divided by 2, which is 6, to 38 divided by 2, which we've already worked out is 19. So again, quick check just to make sure that this can't simplify any further. 3 is common factor of 9 and 6, but it is not a common factor of 19. So that's as simplified as we can make this ratio. So we'll say that's correct. So finally, there are such things as surdic ratios. Now this is a very important idea. So let's introduce it by thinking about a square and an A4 piece of paper, an ordinary A4 piece of paper. Now if I draw a diagonal across my square, then by Pythagoras I know that if this side length is 1, then this must be the square root of 1 squared plus 1 squared, in other words, the square root of 2, so root 2. That's a very important number, root 2. Now, 1 to root 2 ratio is exactly what we've got with our A4 piece of paper. So let's think about our A4 piece of paper. Where's the 1 side? Well, the 1 is shorter than the root 2. Root 2 is approximately equal to 1.414. So the root 2 side is going to be longer, so it's going to be this side here. So if this is root 2, then this is going to be the 1 side. So there's my 1 to root 2 ratio. If I fold my piece of paper in half, then those two sides swap around. But if you look to the side, if you turn your head and look to the side, you've still got 1 to root 2. Fold it again, and you've still got 1 to root 2. And of course this is in proportion with the A4 piece of paper. So you've got an A6 and an A4. So this is the interesting property of the 1 to root 2 ratio. And you can do a similar sort of thing with the square. If you make this the diagonal now, so that this becomes the root 2 side, okay, then we can draw a square on the side here. Let's see, there we go. So that this now becomes the 1 to root 2 ratio. And you can keep iterating this square. So this now becomes the diagonal. So this is the root 2. This now becomes the diagonal. So it's still in the 1 to 2 ratio. And so on, getting smaller and smaller. In fact, creating an interesting spiral. Now, that's a lovely pattern, but what's the importance of this? Well, there was a figure called Hipparchus who discovered what we call the irrationality of ratios, or the irrationality of numbers. And what he seems to have discovered is exactly this property, that when you take something like 1 to root 2, it seems intuitive that you ought to be able to scale up or scale down so that you can get whole numbers, but you can't. You can never get this to become two whole numbers, so two whole number ratio. Poor Hipparchus discovered that unfortunately he was, this was something that his colleagues didn't like, and so what they did was they drowned poor Hipparchus, or so the rumour goes. We know that he drowned, and so the idea is that this was something that just shocked the Greeks so much that they decided to do away with him. True or not, it is true that what he discovered is in fact a fact, and it's a useful fact. If, for example, I thought, well, I haven't quite simplified this, I do need to get rid of this surd, I do need a whole number on both sides, then what would I have to do? I would have to multiply this by root 2, so my scalar would be root 2. So I'd scale up by 1.414 or thereabouts, scale up by root 2. So if I multiply both sides by root 2, I'm going to get on the right hand side root 2 times root 2, well, that's just 2. So I remove my square root side. Great, but I have to do the same to the other side. So times 1 times root 2, I've now got root 2 on the left hand side, and so I haven't got rid of my surd. So whatever I do, however I simplify this, I'm always going to have a surdic expression on one of the sides of my, at least one of the sides of my ratio. And that's called then the irrationality . So you'll come across this, the irrationality of some ratios, or if it's a fraction, then it's going to be the irrational numbers, where the part to whole, if I think of P over Q, is always going to have, for a lot of numbers, is always going to have, say, a square root or a surd on the numerator or the denominator. So, and with some numbers like pi, we don't even get that. Okay, so some numbers are irrational, and poor Hipparchus, it seems, died for discovering this. But from our point of view, it's very useful because we know that, therefore, we can't always get integers on both sides. Okay, now finally, you may come across some interesting names for ratios, and these are called the metallic ratios. So let's just have a look at the metallic ratios. Now, the most famous metallic ratio is called the golden ratio, and we'll save that for another video maybe. What I'm going to look at is the silver ratio. So let's now just explore what the silver ratio might be. If we call this the dangerous ratio, the 1 to root 2, is the silver ratio the same? Well, often it is confused, and I'll show you exactly why it's confused. If I draw this line down here, and I now draw a line across and then dot it over here and here, you can see that this area here looks like the same proportions as with an A4 piece of paper. In other words, it looks like what we've got is 1 to root 2. Now, the silver ratio is actually this ratio here, but it's actually very different to the 1 to root 2. Let's have a look back at this, what looks like the 1 to root 2 ratio. So easy to get confused with these two ratios. If I call this 1, then we can work out what this side length is going to be, and it's not going to be root 2. It's going to be close, but it's going to be different. Let's see what exactly it has to be. So if this is 1, then all the sides must be 1, so this must be 1 as well. So here we've got a side length of 1. Now if that's 1, in fact, let's now use just a single line for 1, otherwise it looks like 2. There we go. So we've got a 1 to, well, by Pythagoras, this must be half of the square root, so it's going to be 1 over root 2. So 1 over root 2. So that's simply by Pythagoras. Okay, so now when I've got this side length of 1 over root 2, what's the side length here? Well, up to this point it must be 1, okay, because this is the side length is 1, and so this must be 1 over root 2 as well. So actually what we've got is, for the silver ratio, we've got, so the silver ratio is, let's call it ratio, okay, 1 to 1 plus these two 1 over root 2's. So it's conceivable that you might get a question something like this, and you're asked to simplify it. The first thing you should realise is that it's not going to simplify to integers. You are going to have some surds, but we can get it a little better than that. So first of all, let's join together those root 2's. So we've got 1 to 1 plus 2 root 2's, like that. But we don't ever, with a surd, want a root 2 in the denominator. So what we're going to do is what's called rationalizing. Okay, we'll end up with an irrational, but rationalizing simply means getting rid of the surdic denominator. So we don't want a surd in the denominator, and we can achieve that. Okay, how are we going to do that? Well, multiplying through by root 2. So if I multiply both sides by, scale it up in other words, by root 2, just as we did before with the dangerous ratio, then what we're going to do is multiply 1 by root 2, giving us root 2, and 1 by root 2 again, giving us root 2, and now plus, well, root 2 times 2 root 2, it means that the root 2's are going to cancel, so I get plus 2. And there we've got the silver ratio. But what I want to do is really, it's fairly simple. If I wanted to express it as though 1 to something, I can simplify this in a different kind of way. Let's have a go at that. So we've now got 1 plus, well, if I multiply both the numerator and the denominator now by root 2, then I'll have 2 times root 2 divided by root 2. Okay, so, sorry, divided by root 2 squared, so divided by 2. Okay. Divided by 2. And what I'm going to do in the interest of space is just erase those 2, because those 2's cancel, giving us 1 plus root 2. Let's just rewrite that nice and neatly. So it's a debate. Is it better to express it like this or this? Which is the most simplified? I guess this looks a bit more simplified simply because it's got less surds in it. But you're never going to get rid of those surds because of this irrational number. But that's the silver ratio. Okay, so it's this area here. Let's erase these. And now we've got a 1 to 1 plus root 2 ratio, which is the silver ratio. Now, poor old Hippasus, who discovered all these things, was apparently drowned for his troubles. So let's just remove Hippasus now and sink him in the water.